Hi, welcome to Databricks Summit, and this is your last session for the day, so we try to get it quick for you to get out for a party. So again, our session is on how AT&T solve ETL problems, challenges as we migrate to the cloud using Databricks and specifically Dbu and Photon. And with me, I have Hao Yu from NVIDIA to help with the project. He will be our co-presenter as well. So as an outline, so I will go to the project background, show some of the data sample that we have, present some of the challenge, and then I will little bit description, and then I will hand over to how to show you how do you get prep for the workload to be GPU compatible. And then he will hand it back to me, and I will go over some of the setup that we have. And then we go over the benchmark number, and then we will get a conclusion. Okay, so as a background, we have many different use cases using AT&T data. I can go into deep into the data that we have, but we have use case like anticipating trends and sentiment. This is where we see how is customer feeling about AT&T products in general using social media and also some of the survey that we got. We have customer insight where we determine what is the age, gender, and profiling customer basically, and customer segmentation, enhancing customer customization, and also the last one, which is very important, is customer churn. We look at various attribute example on why do customer churn, what is the churn rate, and so forth. So that's very important. So for this particular use case, we have this huge data. I mean, not too huge, but this is kind of medium, but for this project, it's a huge data. Let's say that for 1 day's worth of data is about 108 billion record, about 2.1 terabyte. For 7 days of data processing, it will be about 817 billion record and about 16 terabyte. And we throw in about 8 days just to see the variation, but mainly we go for the monthly processing, which is 31 days, about 2.8 trillion record, or 55 terabyte. So for this data, we have about 2 year worth of data. So it's about 700 partition because we divided the data out into by date. So that's come out to be that. Okay, so picture yourself that we have a huge table. This is called main data, and in this table, we kind of like mask out the data, so it kind of look weird. But basically, essentially the column that you'd be interested in is that special column in the middle, where if you look at it, it's kind of look like a URL. Let's think of it that way, right? So it have a URL name and then a port number if there's anything. And then every single categorical ID, those are kind of like foreign key to a category, right? So the example is similar to the one on the right-hand side. So that's how data look like. And this is the large table that has a trillion of record. Okay, so what are the challenges we face? So at the beginning, like last year, when we're using Azure AWS Gen 2, and the timeout is about 60 minutes. So now they increase the timeout, but still, if we process this data and you run a query, if it takes longer than about 2.5 hours, chances are the query will time out and it will say, it just locked you out, so and it just fail. And then, so basically, as you can see, number 2, where when we process 1 day is fine, 7 days we kind of like, sometimes it fails, sometimes it doesn't, but 31 days flat out, we cannot get it to run. And then the query takes too long, so it's expensive. And then also, as you know, is that the way that work is that, let's say that you have a query, we have a lot of cluster, we have a lot of nodes titled like cluster. And so when you run that cluster for a long time, let's say 5, 6 hours, or maybe 24 hours, you're holding up those quotas. So a lot of when people using the same VM type, the job fail because they depend on that quota. And then of course you can request for more, but chances are that it's unpredictable basically. And also last but not least is the cost is very expensive. So we try to resolve it. And this is kind of like a general what the query that we're talking about. So basically we have 5 queries for this benchmark. And this resembles our real production query. I just abstracted so it looked better for this presentation. So basically, assume that we have a main query, like the base query, that we filter out by date. So like for 1 day, that we do a date range 21, weekly is 7 day, and then there's a monthly 31 day. And that is the first filter. And then that will be our base query, and then we have query 1, 2, 3, 4, 5, all derived from the previous query. And not only that, they all derive from each other. So, and then each of those derivation, we have group by for aggregation, and then we also have join, right? So as you can imagine, there's a couple of things going on there. Okay, so at the beginning, when we would see this problem and we couldn't get the 31 day to process, and the natural thing we do is that we have money, so we just spin up bigger cluster to see what happened. So we just add a 63 node, and then we have 128 node, and we just throw in there, and also we just put on Dbu and Photon seeds. Of course, you get the speed is faster, sometimes half the time, or it's even quicker. But the problem is that we don't solve the underlying problem. We just kind of like we improve it, but it's still expensive and all the things. So what happened is that we say, okay, let's step back and figure out how do we optimize this thing before we even throw in the hardware, right? Because we don't just throw money at the problem. So what we did is that we introduced caching. So as you can see from the query earlier, where we have base query, and then we have aggregation, and we have join from the regional base, and also forth. So we can cache those data, and that will help speed up the process. Second is that as you can see, you have category, foreign key. So those are some of them are small table. So we can do a broadcast hash join, where it will improve that. That way we can broadcast the small table to individual nodes, so it's quicker in the join. Another one that we did is that we only run to memory problem because when we run, especially when we do 31 day, because when we pull the data in, and what happens is what people try to do is that you do the collect, so that all your whole result, it would return to the driver, so that you can do array manipulation, which is really bad, because what happens is that those can return, if it's like few thousand, it's fine, but it's when you get to 100,000 or more, you crash the driver. And so what we did is that we used the iterator. There's the process, so that it will help. So that's the command. And then the last but not least is that we use delta leg. So the best thing you need to do is that you have to optimize every time you insert new data. So optimize and run Z order on your data set. Otherwise, the data file, if you inspect it, it will be very small. So after we've done the optimize, our data, the average file size is about a gig. So about 800 meg to a gig. So that's be the number that you want to go by. And after we introduce that, we got everything to improve greatly, and I will show you the number in a minute. So that is the optimization on the Spark in general. So everything should start out with that. And then once we're done with that optimization, now we talk about hardware. So we start looking at using GBU versus CBU versus Photon, which one is better for a certain use case. And then we determine whether we use a large VM or a smaller VM, but scale it wider. So the number of, the size of the VM or the size of the number of nodes is better, which one is better. And also we determine, for example, sometimes you can put a bunch of nodes at first, you still get improvement. But the problem is that sometimes the improvement is too small compared to the price that you put into the number of VM. So maybe you want to lower it down so to get the optimal number. So there's that. We're looking at the over-allocation, underutilization, and so forth. And then last but not least, we use monitoring. So there's a built-in to the Databricks, the Ganglion chart. So we can look at the usage of each of the VMs so that to make sure that they fully utilize. Or else if you allocate with a bigger VM size, sometimes the query doesn't use enough. And then I will hand over to Hal for the next.
Sure. Thanks, Chris. Hey, everybody. So my name is Hal, and I'm from NVIDIA Spark RAPIDS engineering team. So I'm not sure how many people have you heard of Spark RAPIDS? Just raise your hand. No? Okay. So I think most of the people, they are pretty new to Spark RAPIDS, right? So let me just introduce Spark RAPIDS. So basically, everybody knows Spark can run CPU, right? So Databricks is using CPU. Photon is using CPU, right? So basically, we are providing a jar file which can make Spark running on GPU using columnar processing. So that's just in simple words, right? So it's pretty simple. So you just need one jar files and put into the Spark jars folders and enable one Spark parameter. Then suddenly everything is running on GPU. So that's the beauty of Spark RAPIDS. It's also open sourced. You can just Google search Spark RAPIDS. You can find our documentation website. You can find our GitHub. So basically we have multiple GitHub repos. So Spark RAPIDS is our major GitHub repo. You can find some other repos like Spark RAPIDS examples. So you can find some ETL and machine learning, deep learning related example repos using Spark RAPIDS. And we do have Spark RAPIDS benchmark GitHub repo as well, which has a NDS benchmark example there. So NDS is a NVIDIA decision support repo. So it's derived from TPCDS, but it's pretty similar to that. So I would suggest just take a look at our repos on GitHub and Google search that. So yeah, I will start with this slides. So the RAPIDS Accelerator for Apache Spark runs as many operations as possible on the GPU, but not all of them, right? So there could be some features like some functions, some expressions, some data types, some data formats that do not run on GPU. So that's why we need to do this workload quantification. So here are 3 ways to do the workload quantification. The first one is we provide a quantification and profiling tool. So what it needs is just like a Spark event logs from Spark 2.x or 3.x. And of course, we need the Spark 3 plus jar files. And the last thing is we just need the RAPIDS for Spark tools jar, which you can just download from Spark RAPIDS website. It's on the Maven repo, so basically you can just directly download it. So that's the first way. So the second way is there's expand output. So you just need a CPU cluster using Spark 3.x, and also, of course, RAPIDS for Spark jar files. Then you can just do expand plan output based on your data frame. And the third one is if you already have a Spark 3.x GPU cluster, and of course you need the RAPIDS for Spark jar files, you can just run your query directly enabling this Spark RAPIDS features. In the Spark driver log, it will just show you which operators runs on GPU, which operators doesn't run on GPU, those kind of information. So the third way is the most accurate way. So since for AT&T, right, they already have this GPU cluster ready in Databricks. You can spin off a Databricks cluster with NVIDIA's GPU. So basically we just chose option 3 to do the workload quantification for them. So to enable Spark RAPIDS Accelerator in Databricks, it's pretty simple. Here's a link of our documentation website. So basically just put 1 jar files into the Databricks jars folder. That's it. And the second option is you just need to set the Spark RAPIDS SQL expand to OR. So after that, the driver log will show all of the not supported messages or supported messages in the driver log. And then you just run the whole job and connect the complete Spark driver log. So I'm not sure if anybody knows how to connect the driver log in Databricks. If you know, just raise your hand. Yes, so basically, you just set the log directory in Databricks. Then suddenly all of the Spark related logs, like Spark driver log, executor log, and init script logs are inside that log directories. And then after we go to the Spark driver log, we just check if there's any potential functional gaps, right? If there's any, we just go back to our engineering team to file a feature request to add those missing features to fill in those gaps. So the next slide is about AT&T, right? So basically we did the workload quantification for AT&T. So initially there were 2 CPU fallbacks. The first one is in their queries they have a R-like. And at that time, we don't have this R-like supported on Spark RAPIDS. That's why we just go back to our engineering and add that feature. So you just need to specify 1 parameter. At that time is Spark RAPIDS SQL expression .R-like equals to 2, right? But currently in the 2206 release, this parameter is already by default 2, so you don't need to specify any extra parameters. So the second fallback is, so there's a substring optimization in Databricks. So basically, Databricks, they did some optimization for some of the functions, and substring is one of them, right? If you look at the query plan listed here, right? So you see, basically in Databricks environment, they just replace the substring function to a function named the ephemeral substring. So, but to Spark RAPIDS, we don't know that, right? So basically, that's why we have to fall back to CPU to do all of the work. And as a result, we need to disable that feature from Databricks so that the whole query plan can run on GPU. So that's two CPU fallbacks we have to enable to make sure the whole workflow of the AT&T can run on GPU. Okay? And then I will just hand over back to Grace for the rest of the slides.
Thank you. Thanks. Okay, so basically what Hal was saying is just a theory, and then we get into the working, so see it's simpler than it is. So as most people probably seen this picture, this is the cluster creation on Databricks, so I will show you the CBU version. It's very simple, but I want to highlight some of the stuff that we did at AT&T. First thing is that we have policies set so that we have a lot of business unit, different team using Databricks, and so we want to constrain the resource and also the settings. So those, we set policies. So for example, the default for Databricks is that a cluster can be idle for, I think it's like 2 hours or something, and we change to 30 minutes because we don't want to leave it idle for too long. And then also some of the things that, for example, a certain group have assigned to a certain VM. We don't want some group that has like a larger VM versus some group has like a smaller VM node, because you can go to as big as 64 node and 64 core, and we don't want that kind of thing. And so those are the policy. And the second is that on here. Okay, so basically okay, so and then the second one is the enable options scaling. So basically for the purpose of this trial, we leave the enable scaling off, but when you create a cluster, make sure that you check it, so that way you don't want to have your, let's say that you have 35 nodes on all the time. You want to scale as your usage is concerned. But for the purpose of benchmark, we want to be active so that we can compare the query accordingly. And then basically, and then also the almost the last is that you have the authentication. We use pass-through authentication, so the role-based access control, so that when people access the Azure ADSN 2, the storage, it will be credential-based and everything. So Databricks support that. And then the good thing is that with the regular CBU, you don't have to do anything else. That's all we have to do, and we just use it, a notebook. Okay, so for Photon, it's almost the same, where the only difference is that you just go there and check the enable Photon, and what it does is that when you do that, it will scale. It will reduce your. So basically, you can set you choose the VM, but Photon run on a special CBU. So not every CBU has Photon enable. So but if you check that box, what it does is filter your list down to only a subset of CBU core that support Photon. So that's all it does. And then of course you can, and then that green tag that shows you that you're using Photon, because you can use the same VM type, but if you don't have the Photon on, then you don't have the tag. So that means you're not Photon enable. So that's one way to check to see whether you're using Photon or not. And then on the right-hand side, for our special case, we will have to turn this on. Basically, we have to disable the adaptive query, but by default, you probably want to keep it on. So you just, for your case, you probably don't want any of those configuration. But for our case, because we run into some issue, and so we have to turn it on so that to help with our process. Okay, and then this is the GBU. So for the GBU, what you need to do is that you go to choose the ML. When you use the runtime, you choose ML, and then basically you choose GBU for all the items. And once you choose the GBU, and what you do is on the advanced setting, those are the parameters that Hal was talking about. So basically on the website, the RAPIDS website, you will see those parameters. You just cut and paste in there. Basically here, for example, we're using the GBU amount 0.125. That is the concurrency, and then so forth. But those are the settings that you can just keep it by default. It should be good. And then the additional step that you have to do is for GBU is you have to install the RAPIDS jar file. And so basically there is a script online init file that you can copy from, or in this case, that's what it looked like on the thing right there. So that way does it just take that jar file and copy to the Databricks jar folder so that it could run that. And then for the configurations that we use, we do the partition to be 2000 because our data set is huge. So we want to have a large partition at the beginning, but for your case, you can just keep it the default value. Another one that Hal was mentioning, that's the R-like, is that we have to enable it because by default it was disabled. So, but in your case, if you don't use the R-like command, then you don't have to do that. And what happened is that every command that you run on GBU, what it does is that Rapid will have an equivalent operator. And so sometimes some of the operator is not implemented yet, then you will see that. And then what happens is you can open a case on the Rapid team, and then they will try to get it for you, and then you have to enable it here. Okay, so when you run your process, you execute it. Basically, the query is going to be the same across all three platforms. The only difference is the configuration that we have to do at the beginning when we create a cluster. So when you run the query, and then you look at a query plan, for the CBU, it will look on the left. It look normal where you do join and aggregate and all of that. But for the GBU, you will see that everything is initial prefix with the word GBU. So when you see all your query come down and it have the word GBU on all the command, then that means you're good. If anywhere on that operator that it doesn't have the GBU support, it will have a asterisk and it doesn't say GBU, then you know that you're not using GBU operation for that specific operation. And then Photon is the same way. You want to see Photon across on all of your operator. Okay. So once everything is used, then you see it look nice like that. Same thing. The second one, you will see that GBU across down, and then Photon down for the query plan. Okay. So this is the case where on the early time, if you look at the one on the right, you will see that in the middle we box it out where it doesn't say GBU and it say hash aggregate, which is what it does is that it say, since GBU, the Rapid specific, doesn't support that operator, what we do is that we fall back to CBU. And the problem with that is that when you fall back, that means you have to convert your data back into, so GBU use columnar, and then CBU use row, so you have to convert it to row, and then you done the operation and you convert it back to columnar to run the rest of the GBU operation. So that conversion process is bad for you. So that's why you want everything to be GBU client. And when you see such thing like that, what you do is that you open up the driver log, the log.j inside Databricks, and then it will, you search from the bottom up, and then you will see that it will actually say that this operation is not supported, and it will tell you whether you can enable it, because sometimes the operation is there, but it disabled by default. So to optimize, because not a lot of people are using it, so they don't want to enable it, then you just have to enable it by the config file. Sometimes it's not implemented yet, and they will tell you it's not implemented, then you have to create a pull, a request to implement it. So basically, that's what it looks like. Okay, so assume that everything worked well, and and now it's time for us to see how much it costs, because it's it runs fast. You can see the result immediately, so it's faster. But the problem is that you want to see whether that speed is really contribute to the cost, because the GBU and Photon is more expensive than CBU by default. So the speed has to be very much improvement to do that. Okay, so to calculate the cost, the easiest way is that you go to, let's say for us we're using Azure, so we're going to go to Azure, and then there's a Databricks page on Azure that will show us what is the total price. So the price that you see here is actually the price that they will charge you. So basically this price, what it does is it combines with two components. The first component is the compute cost, which is the VM that you use. That's what Microsoft charges you. And then there's a DBU cost, which is when you create a cluster, it will show you how much DBU, and that translates to money. So that two component, DBU and compute, total up, that will be the number that you see here. So if you go to this page right here, it will show you that total. That means that you don't have to do anything else. You just get a total, and that will be the total cost for, let's say for this case, we are using this single node, 8-core DS8 S, that's what an A is, a core, and it costs us about $1 per hour per single node. So when you see that, then it's very easy to calculate. So for example, let's say that I have a query that runs for 4 hours, and in my cluster, I have 5 worker node, and then this will be, because the way Databricks works is that you always have the worker node, and you have to have a single node that is your driver. And most of the time, your driver and your worker are the same. So therefore, you say, if you're using 5 worker node, and you add 1 for your worker, your driver, then it will be 6 node. And then, so in this case, what we do is we just take 4 hours, we multiply by 6 node total, and then we multiply by $1, and then we get the number out to be that's how much it costs. We factor out in 4 hours. Okay, so but what happened is most of the time that page is very limited. It doesn't show you all the range of the VM that you're using, and sometimes they don't have it. And basically, you know, let's say that you're on AWS, how do you calculate it, right? So there's a way to do that. Okay, so again, like I mentioned, is that there are 2 components to the total cost. One is the compute price, and then there is a DBU price. So to get the compute price, you just go to in our case, it's Azure. So you go to the VM, and you would look to say, okay, what am I using for my cluster? What VM? So in our case, for example, the same thing, we're using the DAS something. And then when you look it up, it will say about 38 cents for using 1 node compute. So that is just the VM cost. And then to calculate the DBU cost, what we do is that we go to the Databricks creation page, as you see earlier, and then you just say, okay, I want to create, you know, by default, you can create many nodes, but to calculate it just for single node, what you do is you say, okay, I want to create a single node, and I want to use that particular VM type, and then it will show you what is the DBU. So the DBU that you see there, in this case, is for only single node. And then you take that DBU, and then it's dependent on your, whether you run an interactive cluster. That, for example, in the middle, you will see that for interactive cluster all purpose, it will cost about 40 cents per DBU. So that number of DBU will have to multiply by this factor to see how much it costs. And if you run a job, it costs you about half of the DBU the thing. So, and then, you know, and also if you do a premium tier, it costs you more. The good thing about all of this is that you calculate everything in components. So basically what happens is that your organization may have some discount for DBU and then some different discount for compute. And this will help you do that calculation. And then once you multiply that all up together, then you will get the price, you know, how much compute you got, multiplied by the factor, you get the compute price. And then also, we recommend that you do it per node, because that way, when you scale up your cluster, you can just multiply up better. So in our case, we calculate that it costs about the same thing with the previous, where we add all those components up. It's about $1 per node per hour, right? So with all this calculation, so now let's come back to our benchmark. So originally, we start out with 95 node, 8 core, and then so we run the ETL. Again, you see that for the daily, it costs about $55. For weekly, it costs about $389 to run. And then for the monthly, we couldn't get the result at all. And so after we optimize, you know, we do the caching, we do the iterator, and then we do the Z order and all of that. So now on the same CBU, we was able to get it down to 70. The speed is, you know, is about 3 times faster, and then also so in terms of the cost, we bring it down 71%. But that is only for the optimization, right? So and then we take that number and say, okay, we improve everything, but our hardware might be, you know, too oversubscribed and so forth. So therefore, we say, okay, with this, we adjust the cluster size, and then we up and down, and then we also put it on CBU and GBU and Photon, and then we see the difference. So basically what happens is that, you know, you can have a really large cluster size you run. It's much faster, but then it's still expensive as well, and so we reduce it, and then we get to the yellow one. The yellow one are the one that optimal number. And then we run it against Photon with the same, and then this is what we got. So basically for Photon, the price that we currently use is the price after the promotion. So basically it's 3 times faster So it's improved on the base query, and also the cost saving is, but because it's expensive, so the cost is 27% saving. And then for the GPU, the speed about the same with the Photon, 3 times faster, and the cost is about half of that. Okay, and then so for the conclusion, we have for Photon 3 times faster than CPU, but because of the price, depending on your organization, you may have a cheaper discount or something. But if we're using the normal pay-as-you-go price, then it will be about 27% improvement in price. Versus for GPU, it's 3 times faster, but since the GPU price is cheaper, then it's about half the price that you would have. Again, you have to constantly make sure that you don't oversubscribe, allocate your resource, and so you adjust it, and that will give you maybe additional saving, basically. Okay, so what's next? So we plan to continue with NVIDIA partnerships, so we can do like machine learning. So we look into XGBoost, and then we look into additional ETL as well, and then some other product that NVIDIA provide. And also we working with S3 to do the geospatial for large data set.
So I haven't looked at the web page of the Spark Rapids. So it sounds like Spark Rapids does not support all the functions, if I heard correct. Is there a simple rule or statement what kind of functions are not supported by Spark Rapids currently? And maybe a specific question is, does Spark Rapids support UDF functions?
Yeah, maybe it's a question for me, right?
Yeah.
So so good question. So for Spark Rapids, we have a documentation website. So in the documentation website, we have one page to show all of the supported operators. So you can find an exhaustive list for all of the supported operators. So, but in the meantime, we are trying to add more and more based on the customer's use case, right? So it's adding pretty fast.
And one thing I want to add to that is that NVIDIA team is very responsive. So if you run into an operator that is not supported and you find it out from your log, you just go to the request, send it to them, and then they will get back to you. And then we was able to get a lot of our operator implemented within weeks. So.
Yeah, we are pretty fast on that. Yeah, that's a good question, right? So UDF is more like a black box to us, right? So we do support a Scala UDF to some extent, right? So if it's very complex ones, you can talk to us. There's one way to rewrite the Scala UDF using RAPIDS UDF. So there's one features, right? For the Python UDF, we do support some of the Pandas UDF on GPU as well.
Time for one more question.
To use Spark Rapid, do you have to write your query in Java or Scala, compile down to a JVM, to a jar file, or does it support Spark? PySpark, Python.
So I'm not sure if I understand the question. So you mean we need to use
basically the query will be the same. So you're using either regular Spark, the regular Spark API, or you're using the normal query like select star or something. And it automatically supported on GPU. You don't have to do anything, and Photon the same way. The only difference is that you just have to make your cluster set up either GPU or Photon or something.
Okay, thank you.
I think we're at the end of the session, so thank you everyone so much for coming out. I think if there's more questions, maybe you're able to attend to those outside, but in the meantime, thanks everyone.
Thank you.
Thanks, everybody.